Let's look at Leibniz's test or Leibniz's test. In all the tests we have seen till now, the terms were non-negative. That is, a sub n is greater than or equal to 0. To ensure the positivity, we had tests taking the magnitude of a sub n. Leibniz's test works for alternating series. That is, the general term of the form minus 1 to the power of n minus 1 times a sub n, with a sub n greater than or equal to 0. So basically, the signs and the term are being separated. So what the test says is the series minus 1 to the power of n minus 1 times a sub n, where a sub n is greater than or equal to 0, converges if there exists m in n such that a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to m. Basically, what all this means is that a sub n plus 1 is less than or equal to a sub n eventually. Limit as n goes to infinity of a sub n is equal to 0. What the Leibniz's test says. Now, in an alternating series, we have two parts, the sign part minus 1 to the power of n minus 1 and the magnitude part a sub n. That is, a sub n is equal to the magnitude of u sub n for all n. Leibniz's test works on the magnitude part of the terms. Secondly, even though the theorem is written with limit as n goes to infinity of a sub n equal to 0 as the second condition, we should check it first since that is the necessary condition for any series. So now let's actually see how it works. So let's say we have this alternating series, a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 and so on. Let S sub 2n be the partial sums of 2n terms. So S sub 2n is equal to a1 minus a2, a3 minus a4 plus dot 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 plus a sub 2n minus 1 minus a sub 2n. So this is the nth partial sum of 2n terms. Since a sub n is eventually non-increasing, we have a sub 2n minus 1 is greater than or equal to a sub 2n, which implies a sub 2n minus 1 minus a sub 2n is greater than or equal to 0, which implies that each of these bracketed quantities are greater than or equal to 0. So here a1 is greater than a2, a3 is greater than a4, a sub 2n minus 1 is greater than a sub 2n. So which means these quantities are all greater than or equal to 0, which implies that the partial sum s sub 2n is greater than or equal to 0. So the partial sum s sub 2n plus 2 is equal to s sub 2n plus a sub 2n plus 1 minus a sub 2n plus 2. So s sub 2n plus 2 minus s sub 2n is equal to a sub 2n plus 1 minus a sub 2n plus 2, which is greater than or equal to 0. Which means s sub 2n plus 2 minus s sub 2n is greater than or equal to 0. Which implies s sub 2n plus 2 is greater than or equal to s sub 2n. So, which means the sequence of partial sums s sub 2n is monotonically increasing sequence. Now we do the grouping like this. We keep the first term as it is and then group do the grouping. So since a sub 2n minus 1 is greater than or equal to a sub 2n, eventually, and hence these quantities, that is the bracketed quantities, are greater than or equal to 0, which implies s sub 2n is less than or equal to a sub 1, since all the remaining terms are being subtracted from a1. which implies that S sub 2n is being bounded by 0 and a1. So thus the sequence of partial sums S sub 2n is monotonically increasing and bounded. So since it is bounded, let limit as n goes to infinity of S sub 2n be equal to L. Then the limit as n goes to infinity of S sub 2n plus 1 is equal to limit as n goes to infinity of S sub 2n plus A sub 2n plus 1. So limit as n goes to infinity of S sub 2n plus 1 is equal to, we are splitting this using algebra of limits. Limit as n goes to infinity of S sub 2n plus limit as n goes to infinity of A sub 2n plus 1. Now, this is L and this goes to 0. That means the limit of A sub 2n plus 1. Remember, we have already shown that the limit as n goes to infinity of A sub n equal to 0. So this will be 0. So limit as n goes to infinity of S sub 2n plus 1 is equal to 0, which implies that the series minus 1 to the power of n minus 1 times A sub n is convergent. Let's solve some problems. Let's say we have the series u sub n is equal to 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5 and so on. Let's write it in this form. The series u sub n is equal to series minus 1 to the power of n minus 1 times 1 by n. So here A sub n is equal to 1 by n and is positive for all n. I'm sure you remember that this is nothing but the harmonic series. So limit as n goes to infinity of 1 by n is equal to 0. The necessary condition for convergence of any series is satisfied. And more specifically, the second condition of Leibniz's test is satisfied. Now let's take the next term, A sub n plus 1. That would be equal to 1 by n plus 1. We need to figure out whether A sub n plus 1 is less than or equal to A sub n, eventually at least. So let's see, 1 by n plus 1 is less than or equal to 1 by n. So here the left hand side has a bigger denominator. That means it is a smaller quantity, LHS. So which implies A sub n plus 1 is less than or equal to A sub n for all n. Strictly speaking, it is less always. For the first term, it will be 1 by 1 plus 1. That is 1 by 2 is less than or equal to 1 by 1. But as part of the standard way of showing it, we write it as less than or equal to A sub n for all n, which means that the sequence of the magnitudes A sub n is monotonically decreasing. So both conditions for convergence are satisfied. Hence, the given series is convergent. Now let's look at the second problem. Series u sub n is equal to series minus 1 to the power of n minus 1 times n divided by 2n minus 1. So here A sub n is equal to n by 2n minus 1. And this is positive for all n. Now limit as n goes to infinity of A sub n is equal to, if we work out the limit, we get 1 by 2, which is not equal to 0. So that means the necessary condition for convergence of any series is not satisfied, or more specifically, the second condition of Leibniz's test is not satisfied. That means we don't even have to think in terms of Leibniz's test. Just based on the necessary condition for convergence of any series not being satisfied, we can say the series is divergent. So, important point with respect to this problem, that just because a series has alternating signs doesn't mean you require the Leibniz's test at all. Just make sure that the necessary condition is satisfied. And then if it is satisfied, then only we require Leibniz's test. Now let's look at the next. Now we have a series u sub n equal to 1 by 2 cube minus 1 by 3 cube times 1 plus 2 plus 1 by 4 cube times 1 plus 2 plus 3 and so on. So we have a sub n is equal to 1 plus 2 plus 3. For the nth term, it will be 1 plus 2 plus 3 plus dot 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 plus n divided by this is n plus 1 cube. So we have the nth term, a sub n. Now, the numerator is the sum of first n natural numbers, for which we know the expression is n times n plus 1 by 2 and multiplied with 1 by n plus 1 cube to incorporate it into our a sub n. Now n plus 1 and one of the n plus 1 gets cancelled and we are left with a sub n is equal to n divided by 2 times n plus 1 square. Here again a sub n is positive for all n. Now let's take the limit of this term as n goes to infinity. Going through the steps of finding the limit, we notice that it is equal to 0, which means necessary condition is satisfied. Let's come out with the next term. A sub n plus 1 is equal to n plus 1 divided by 2 times n plus 1 plus 1, that is n plus 2 square. And now we have to figure out whether a sub n plus 1 is less than or equal to a sub n. And if yes, then we will be in a position to arrive at a conclusion. So let's cross multiply. First of all, 2 and 2 get cancelled out. N plus 1 square times n plus 1 gives us n plus 1 cube is less than or equal to n times n plus 2 square. Opening up the brackets, we get n cube plus 3n square plus 3n plus 1 is less than or equal to n cube plus 4n square plus 2. Simplifying it, we get 3n is less than or equal to n square plus 1. So which means that this is true for all n greater than or equal to 3. And that is how this eventually word comes and what this statement means. So a sub n plus 1 is less than or equal to a sub n eventually. The second condition is satisfied, which means that the series u sub n is convergent. So that was Leibniz's test. Now, if you found this session helpful, please do like, share, and subscribe. Comment suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now. Bye.